Hi everybody. Today we are going to start chapter 9, which is focusing on alkynes, their reactions and how we make them. And this will be a nice follow-up from the previous chapter where we did a ton of alkene reactions and their synthesis, and you will see similar reactions with alkynes just due to the similar structure property relationships that pi double bond versus triple bond. And so a lot of this chapter will be a nice review for you with some slight changes of reagents and that sort of thing. So, and then towards the end it'll be a really good introduction to multi-step synthesis. Okay. So what exactly is an alkyne? Well, hopefully you remember all your functional groups, and you said that an alkyne is a triple bond or a carbon-carbon triple bond. Okay. And like I just said, it's this particular chapter will provide an introduction for organic synthesis. And I've already said this before in the lecture and as well as the laboratory. It's our duty as organic chemists to be able to synthesize, for example, pharmaceutical drugs that will help cure a patient in a very cheap and a cost-effective way. And the only way to do that is to design syntheses that are efficient, high-yielding, and come from simpler organic molecules. So you're always going to start small and then grow to something big, right? And from here on out, like I said, we're building our toolbox of useful organic reactions. So don't forget the reactions you learned in the previous 2 chapters. You're going to be using them over and over and over again. So it's really critical that you practice your reactions and their mechanisms, the ones that I go over, on a regular basis. So not just like right before the test or right before the final, but really, every few days, just sit down and just review over the reactions again. Because remember, organic is like learning a new language. And in order to be successful at learning that new language, you need to practice it daily. And that's why study groups are useful, or if you don't have time for a study group, talking yourself through the reactions, kind of like the way I talk you through them, and practice writing them, will be very useful of your time. Okay? So when I start any kind of new functional group, I always have to teach you how to name them so that we are consistent when we are naming our compounds. And so because it's an alkyne, the hydrocarbon rules apply with YNE or "-ine" as the suffix indicating an alkyne if that's in your particular compound. And we always number the chain with a triple bond, so it's set to the smallest number possible, and that's before the branching rule. So this is the same thing as the alkene. You always kind of number the alkene, smallest number possible versus branching. Now, I don't want you to fall into this trap and saying it has to be the smallest number possible, because eventually I'm going to introduce you to alcohols and aldehydes and ketones and functional groups that have higher priorities than alkenes and alkynes, okay? But for right now, you're always treating the multiple bonds, so it gets the smallest number possible, okay? And if you have both a double and a triple bond in your structure, then alkenes, you always want to work on numbering, so give the multiple bonds the smallest number possible. But if they're equidistant, so you can number from either direction, the alkene will take priority, and I'll show you that on the next slide, okay? So if the compound has a double and triple bond, then number so that both have the smallest number possible. Kind of like branching, right? However, if they are equidistant from both ends, so it doesn't matter which way you number them, then alkenes have higher priority. Than alkynes. Okay? So let's practice, and like I said, with nomenclature, very easy points. The more you practice it, the better off you'll feel, especially for tests. You're like, yes, I got this. So really want to practice your nomenclature problems and try to make up other nomenclature problems to test your study group or even to test yourself. Like what kind of structure could Dr. P draw that I would have to name, you know? You can come up with your own problems. Start thinking like the professor. It'll definitely be very useful. Oh, my apologies. It did not go through very well here. So I'll finish drawing them out for you. It must have gotten cropped. So it's black here. So this structure looks like this. Okay, and this structure. Okay, and then this one just had its triple bond kind of trimmed off. There we go. Okay, so pause the video and try to draw the structures of these compounds. And you draw the structures, but try to give the IUPAC name for the structure of these compounds. Okay. Hopefully you've had a chance to work on this, and you're just checking your work after you've paused the video, right? No cheating. So what you want to do here is find, first off, the longest carbon chain, right? So we're going to look here on the first one, and what's the longest carbon chain you found? Looks like 1, 2, 3, 4, 5, 6, 7, 8. So we found something that potentially could have been an octane, right? However, it's not an octane anymore. It has a double bond and a triple bond. And when that happens, the suffix does get a little tricky here. You drop the A and E, and it's an octene ine. Okay? So that's how you would write the suffix name. I know you're thinking, why is it not E-N-E? Because we're starting off with this, and Y is kind of like a vowel sound. And so we're not going to have E and Y next to each other, so we drop the E, and then that's why it has E-N-I. So E-N-Y-N-E. So be careful with your spelling. Make sure you're practicing that. And now we want to number. So we kind of have an idea of what our suffix name looks like, but we need to number. So 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to number from the other direction. 1, 2, 3, 4, 5, 6, 7, 8. So in the red direction, it looks like we could have a 3, 5. And in the blue direction, it looks like we have a 3, 5. So they are equidistant from one another. The alkene will take priority here. And so we will have an oct 3-ene 5-ine. Right? So an oct 3-ene 5-ine. And that's where the new naming system is really useful. It would have been really confusing to use the old naming system, right? Where it would have been like 3, I think technically it would have been 3-octene 5-ine. You still had to put the 5 in front of the ine. But it's just nicer with the new naming system where the numbers are directly in front of that little suffix ending. Okay, so there's no confusion at all possible. We also have a 6-methyl. And so the way we would write this name is 6-methyl oct 3-ene 5-ine. Are we done yet? Nope, we are not done yet. What do we have? We have stereochemistry, right? Of what bond? Of the double bond. And we have to assign E or Z. So I'm going to snip it, right? I'm going to snip it in half and identify is this higher or lower. This one is higher priority. This is lower priority. and this one here is higher priority, and the hydrogen hanging up here is lower priority. So the higher priorities are on the same side. What kind of stereochemistry do we have? Z stereochemistry. Good. So therefore, it would be 3Z in parentheses hyphen 6-methyl-oct-3-ene 5-ine. Okay? So don't forget stereochemistry. Now, do triple bonds have stereochemistry? Do you think? I mean, just looking at it. No, they don't. So they don't have stereochemistry that we have to worry about. So that makes alkynes a little bit easier. Alkenes do, but alkynes we don't have to worry about stereochemistry. All right, let's do the next one here. So we have a very interesting molecule here that has 2 triple bonds, and it's a ring structure. How big is the ring structure? 1, 2, 3, 4, 5, 6, 7, 8. So it looks to be 8 carbons long. So it looked like it would have been a cyclooctane, right? However, it's not an octane anymore. It has 2 triple bonds, so we would say it has a diene. And so we're going to drop the NE and keep the A because we're starting our suffix with a consonant. So this is going to be a cyclooctadiene. Okay. And we have to number, right? So that's going to be what we got to do. And so 1, 2, 3, 4, 5, 6, 7, 8. We must number across the triple bond just like you have to number across the double bond, right? And then number it the other way. 1, 2, 3, 4, 5, 6, 7, 8. So the purple way I could have a 1, 4. The green way I have a 1, 4. Does it really matter here? No, it doesn't matter which way we number it. There's no branching or anything for us to decide which way. Okay, so therefore the name for this one is a cycloocta hyphen 1, 4 hyphen diene. Okay. Excellent. And actually, I did make a mistake. There's 2 O's here. Sorry. There we go. Okie dokie. Don't forget the word cyclo. That's the most common mistake I see with students in their cyclic structures. And also numbering, because numbering can be tricky. It's like, where do I start? For right now, the multiple bonds need to have the lowest number. Then worry about branching. Okay? Now we have the last one here, and how many carbons long do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like it would have been what? Decane, but not really just an alkane anymore. It has 2 triple bonds, so therefore it's a decadiene. And let's number. We can number it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do a different color and see if that changes anything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So which way would you number it? The purple way or the orange way? Hopefully you said the purple way. And why is that? Well, the triple bonds are equidistant. You either have 1, 9 or 1, 9, right? So then you follow on what rule? The branching rule. And I've noticed that the ethyl group here could either be a 5 or a 6. Well, we definitely want to give the branching the lowest number at this point in time. So it'll be a 5 ethyl. Okay? So let's combine both of those together and say that we have 5 ethyl deca hyphen 1, 9 diene. Okay? And we had to, so a lot of times students always ask me, do I have to include the number 1? Yes, you do, especially for example when you have 2 functional groups. You're not going to just indicate that you have a group at number 9 or starting at carbon 9. You also want to indicate that it's also starting at 1. Okay? The only way that you maybe can ignore having one is if there's only one triple bond is at the end. But I would be safe, and I would just go ahead and number. Like, there's no harm in doing it. You know how to do it. It's not like it takes any extra time, really, to write down number one. So just be safe, okay, and just do it. Okie dokie. So keep practicing your naming. Now you know how to name double bonds and triple bond containing compounds. Triple bonds don't have stereochemistry, so always ask yourself, do I have stereochemistry to worry about? Double bonds, definitely we do, E and Z. And if I put a chiral center in there, you have to worry about that too, right? So R and S. So just make sure you're practicing your stereochemistry for the next exam. So remember, when I start teaching you a new functional group, I always show you how to make them first and then all the reactions thereof. So just like alkenes, the way we prepare alkynes is through elimination reactions. But instead of just using an alkyl halide, we have to use a dihalide. Okay? So if we treat a 1,2-dihalidoalkane with KOH or sodium hydroxide, which are what? Strong bases, it produces a twofold elimination of the hydrogen halide and the alkyne. And so this one, remember, we're going to study more about elimination reactions in Chapter 11. So we'll get to that a little later in the game. Okay? And vicinal dihalides are available from addition of bromine or chlorine to an alkene. Okay, so let's just go through that here. We have an alkene here, and let's say I want to make a triple bond, because I have to have some sort of 1,2-dihalide, right? Well, if I did a bromination of an alkene, I would get a 1,2-dihalide. And then if I use base, I can use base to pull off a proton, and I'll go through the mechanism a lot later, and it kicks off this bromine here. That's one equivalent of base. But if I use another equivalent of base, it can pull off this proton, put those electrons there, and kick off the bromide. So you can see two arrows coming here, and that's going to make, a triple bond. We eliminate potassium bromide and some water when we go through this process. Okay? You need to know how to make them and what reagents that were needed to make alkynes. So just make sure you're practicing that. And like I said, we'll go through the more nitty-gritty mechanistic details later. I did want to go over what vicinal means. Vicinal stands for two groups bonded to two adjacent atoms. Adjacent meaning right next to one another. So we have a 1,2-dihalide, then we would just simply say that's a vicinal dibromide or dihalide. Okay? Later on you'll learn the word geminal, which means they're directly attached to the same carbon. So it's important you know the difference in vocabulary, like know that vocabulary word. Okay? Notice how when we do this reaction, we needed two equivalents. And then the ethanol is just going to be your solvent. And solvents play a big role in these elimination reactions. So it's important that you learn, what's a good solvent for this type of elimination? Well, ethanol is, in this case. Okay? So that's how you prepare alkynes. How are we going to react them? Lots of reactions we're going to go through. Not as many as alkenes. So they're not as versatile as alkenes, but still pretty useful. Okay? Just like alkenes, alkynes undergo addition reactions. Okay? Electrophilic addition. So you already feel comfortable with this mechanism by now. You've been studying and watching the lectures and practicing homework problems and working on the work session already. So, make sure you understand that, because that will make your chapter here a lot easier for you. So if we did an addition reaction, and let's say we only did it with one equivalent of a halogen, for example, like bromine, then we would just get one addition, right? The trans kind of dihalide that you would expect, right? Except this is not just any normal trans 1,2-dihalide. It actually still has a double bond because only one pi bond reacted with that one equivalent of bromine. Okay? However, if you were to add another equivalent of bromine, then it would add again to that double bond, and you would make a tetrahalide. So this is 1,1,2,2 tetrabromobutane. So depends on the number of equivalents that you use. And be careful, because when I give you a predicting products, be mindful. If I say 2 equivalents, you need to make sure that you understand, oh wait, I know that one equivalent does this, the second equivalent does that. So if I'm being that specific, it might be a clue to say, okay, really think about the product that you're drawing here. Did you really react it fully and completely? Okay. Stereochemistry obviously matters with the first addition, trans, kind of similar to what we've seen in the previous chapter. Regiospecificity also is important. So it does follow Markovnikov's rule. So when you do, for example, 2 equivalents of HBr and ether, for example, as your solvent, then the bromine's going to add to the more substituted side, right? The halogen adds to the more substituted side. So just be careful with that when you're predicting products. And your textbook has some great figures for example reactions for addition reactions to alkynes. Okay? But I wanted to move on and talk more about the electronic structure, since a lot of this is review, and we'll get to practice it more in the work session. So we know that an alkyne is a carbon-carbon triple bond, and that the hybridization of the carbon atoms are sp hybridized, right, with 2 unhybridized p orbitals, like a px and a py, or py and pz, whatever you want to call them. We have 2 unhybridized p orbitals, and those form the pi bonds. And this is all from like chapter 1, chapter 2. So it's really important that if it doesn't make sense to you, you need to review over those chapters. And these particular sp hybridized atoms form 180-degree bond angles, and so that's why we have a linear geometry. The bond, we're sharing 6 electrons in a triple bond, so the bond is shorter and it is stronger than single or double bonds. In our bond energy, or the energy needed to break a bond in acetylene, for example, acetylene is the structure here, requires 318 kilojoules per mole, whereas ethylene, it only requires 268 kilojoules per mole. So if we were to break it in half, that's how much energy it would be required. Now, I always get this question every single year, and it's a really, really good question, and that is, well, Dr. P, you say a double bond is stronger than a single bond, but at the same time, a double bond is more reactive. And they would think, well, if it's stronger, it'd be harder to react. But remember that in a double bond, as well as a triple bond, those electrons are farther away from the nucleus, and they are quite nucleophilic. You can see the red spot there. It means it's more nucleophilic, right? And because of that, whenever we add anything else, like an electrophile, the double or triple bonds want to react, okay? So don't get confused there. Yes, if I just wanted to break a triple bond on its own, it would be hard to break. But if I have something else it's attracted to, it'll want to still react, even though it's a strong bond, okay? And like I just said, this is kind of a repeat from 2 slides ago, giving you an example of electrophilic addition. You can do the same thing with chlorine, HBr, HCl. But with the bromination here, you get that trans 1,2-dihalide, E stereochemistry. And then if you added a second equivalent, you get the tetrabromine. So just make sure you are practicing these. And you may be wondering, well, what kind of mechanism does it undergo? I mean, does it still have the bromonium ion like we saw before in chapter 8 and particularly in chapter 8, right? So, as a refresher, the first reaction I ever taught you was electrophilic addition of a double bond with HBr. And, we did the reaction, and the double bond pulled off a proton and then formed a carbocation, and the bromide attacked. To make an alkyl bromide, for example. And in this case, it did go through a carbocation, not a bromonium ion. It's different if you react it with bromine, Br2, right? But if we do the same reaction with a triple bond, we just react one bond at a time. We end up with a vanillic carbocation, okay? And then the bromide attacks, and it wants to have the more substituted carbocation, like always. And we would make our vanillic bromide, and then we can go ahead and react it again if we need to, or we can stop here. We can isolate this product, okay? So that's nice. So we have some flexibility there. Now, what I did want to point out, that is a vanillic carbocation is not as stable as an alkyl carbocation, and it has to do with the hybridization of the atoms, this being sp2 now, and this being more, well, no, this is being more sp2, I'm sorry, and this is being more like sp. It's just not as stable of a carbocation. So this reaction probably is going to be not as high yielding as a double bond reacting. And if you try to make a primary vanillic carbocation, it's never going to happen. Okay? But you can do secondary. But like I said, it's just a little bit more unstable. Okay? You're also going to hear me refer to vanillic or vinyl groups, and vinyl groups are derivatives or similar compounds of ethene, which one hydrogen is replaced with some other group. And so when I say a vanillic carbocation, I'm saying that the carbocation is on the double bond, okay, at least one side of the double bond. Okay, so another vocabulary word for you to learn, vanillic or vinyl. Okay. So let's do an example, a couple examples. Pause the video. You can go through the mechanisms. I challenge you to do that. Try to predict the mechanism, what it looks like. They're pretty straightforward. We just kind of went through an example of one. And then predict their products and come back and check your work after you've done it all. Okay? Hopefully you've had a chance to do that. The very first one, we're only adding one equivalent. And so I always tell students to number or kind of count 1, 2, 3, 4, 5. So it looks like I have 5 carbons, right? If it's only one equivalent, that means that only one bond's reacting, so I'm left with a double bond. And it follows what kind of regiochemistry? Markov-Nakov's rule. Good. So therefore, the bromine goes on the more substituted side. Good. And that's your product for the first one. And the second one, we have 2 equivalents of Br2. So what kind of product are you going to make? A tetrabromide. Good. Oh, whoopsie. And you don't have to worry so much about the stereochemistry here. I'm trying to get you to practice and think in 3D. But are these chiral centers? No, so you don't have to worry about it. Same thing with the first one here. Is this a chiral center? No, because it's sp2 hybridized, right? Chiral centers means we need to at least have sp3 hybridization, right, in 4 different groups. Okie dokie. So make sure you practice those addition reactions, electrophilic addition with HBr, and practice 1 equivalent versus 2 equivalents, and then also Br2, 1 equivalent versus 2 equivalents, and knowing that these same reactions happen with HCl and Cl2 respectively. Okay? So kind of running parallel to the last chapter, we talked about electrophilic addition and doing halogenation reactions, then we followed up with hydration. Or making alcohols. So same thing we're doing here. I'm going to talk about the hydration of alkynes. We can do a similar type of reaction, oxymercuriation, where mercury 2 helps catalyze the Markov-Nakov oriented addition. And we can also do hydroboration oxidation, which gives the non-Markov-Nakov product. Okay, so either way. But I wanted to point out here, and I'll kind of walk you through this, that First, the reagents are different, so when you're making your table, you want to make sure you make note of that. Whereas before it was, step 1, mercury diacetate, water, and then like THF for the solvent. And then step 2 is sodium borohydrate, right? It's not the same for alkynes. We don't need it to have sodium borohydrate. We're going to have water, we're going to have sulfuric acid, and then mercury 2 sulfate. And so we can use the acid to help remove the mercury and replace it with hydrogen. Okay? Now this reaction only does once, like one addition. So it has the alcohol on the more substituted side of the double bond, and this is called an enol. It's important for you to recognize that as an enol. How do you remember that? Well, it has a double bond and an alcohol, OL, attached to double bond, so it's an enol, right? Enols are not very stable, and in equilibrium, they like to do a process called tautomerization, which I'm going to go through in a little bit. And they will tautomerize so that this alcohol group essentially turns into a ketone. And the hydration of, oxymercuration of triple bonds, ideally you're going to be looking for something that is a methyl ketone. Only if you have a terminal alkyne. It works best with terminal alkynes, okay? So let's talk a little bit about the mechanism. Maybe knowing the mechanism or seeing it will help you remember what's going on. It's different. It doesn't have the mercurinium ion. Alkynes do not react with an aqueous protic acid. So we're okay with that. And that's the reason why we couldn't do it with the double bonds, because they're reactive with acid, right? The mercuric ion is a Lewis acid catalyst that promotes the addition of water in Markovnikov orientation. And the immediate product is a vinylic alcohol, or an enol, which spontaneously transforms into a ketone due to this whole cool process called ketal-enol tautomerization, which we'll go through. But before that, I just wanted to show you the basic mechanism. So let's draw our triple bond. It's going to act as our nucleophiles. That's why I'm initially drawing it in red. And we're going to react it with mercury 2 sulfate. And the double bond's attracted to what? Or the triple bond is attracted to the mercury, right? So the triple bond's attracted to the mercury and wants to form a carbocation. And the carbocation is going to form on what side? The more stable side. So the carbocation prefers to be on the more stable side, and the mercury is on the less substituted side. Okay, so that's an intermediate. We are reacting with water, and water can act as a what? As a nucleophile. So water is going to come in and attack the carbocation. So this is where you get your hydration step in, right? So let's go ahead and draw our intermediate. An oxygen with 1 lone pair and 3 bonds has a what kind of formal charge? +1. And then the mercury is still there. Now that, water that's attached doesn't look too happy, so what do you think is going to happen? You've seen it before. Another water molecule is going to come in and act as a base. Good. So these electrons come down, pull off this hydrogen, and these electrons go onto the oxygen. Okie dokie. And we generated some acid, or the hydronium ion. And one of the last steps here, and these are still intermediate, so brackets around them. And one of the last steps is that acid, basically, the one that you generated, helps to cleave off the mercury. So we're left with what kind of product? It had a special name. Let me finish drawing it. Oh, no. Oh, whoopsie. Sorry about that. So we're going to use blue. There we go. So it has an alcohol on a double bond, and it's not very stable as is, so this is called an enol, right? And the enol is going to convert, it's an equilibrium process, it's going to convert into its keto form. Where that alcohol turns into a ketone, in this case here. Right? And more specifically, a methyl ketone. All right? Make sure you practice this mechanism, you know it. It is a little bit different than the one we've done before with alkenes, where we go through a mercurinium ion, so you just want to make sure you practice it, okay? Now, coming back to this keto-enol tautomerization, and this tends to be initially something that students struggle with, but once they get the use of it, it makes sense. So isomeric compounds that can rapidly interconvert by the movement of a proton, this is what's happening, are called tautomers, and this particular phenomenon is called tautomerism. And enols can rearrange to their isomeric ketone by the rapid transfer of a proton from the hydroxyl to the alkene carbon. And the keto form is usually so stable compared to enol that only the keto form is observed in many cases. Okay? So your textbook doesn't go through the mechanism, but I found one for you. Basically, this is an enol and the presence of acid, right? When these electrons come down to form a double bond, these pi bond pulls off a proton. These electrons go on to the oxygen to form water. Water comes in and deprotonates that protonated ketone, and then you're left with the ketone. It's in equilibrium, okay? But the keto form is more stable, and so therefore it's less favored. So you can see how the hydrogens kind of transfer and the double bond moves up there. You don't necessarily need to know the mechanism, but it might help you in order to predict, what kind of keto form am I going to have, instead of just memorizing it, okay? Just like we talked about before, this particular reaction wants to follow Markov-Nakov regiochemistry, right? However, if you have a triple bond, and if the alkyl groups on either side of this triple bond are not the same, then both products can form, right? This is not very useful for reaction. So if we have an internal alkyne, then we could have a carbonyl on this side or a carbonyl on that side. So we could have two products form, and having a mixture of products is very, it's not desirable, because then you'll have to purify it, right? So we pretty much, for this reaction, try to react with terminal alkynes only, because then that way the only product you get is a methyl ketone. And that's something that's unique and characteristic to this reaction. If I give you a multi-step synthesis and you notice, oh, this has a methyl ketone in it, then more than likely we probably made that methyl ketone from oxymercuration of a triple bond. So you have to think backwards and say, well, how do I get to that triple bond? Okay? Just like we can do oxymercuration, we can do hydroboration, and followed by oxidation and hydrogen peroxide. The reagents are the same here. It's the borane, BH3, THF, and the second step. So this is step 1, and this is step 2. Is hydrogen peroxide, water, and sodium hydroxide, or some type of base. Don't want to add them in all at once. That's not going to be good, right? So we have to add them in 2 steps. Okay. In this case here, I am showing you an internal alkyne. It works because it's symmetrical, but like I said, it's very rare that we use it. But basically, the BH3 would want to add to the less substituted side if it can, and then hydrogen peroxide helps to convert it into an alcohol like we saw before with hydroboration of alkenes. However, once we form the enol, then it tautomerizes into the keto form. Okay? And if it's a terminal alkyne, you will end up making an aldehyde versus a methyl ketone for the oxymercuration. You can see it here. Okay? Hydroboration and oxidation converts terminal alkynes to aldehydes because the addition of water is non-Markovnikov. The product from the mercury to catalyzed reaction converts terminal alkynes to methyl ketones. So that's how you can distinguish between the two when you're predicting products or using them as tools for multi-step synthesis. Okay. Don't worry too much. It does make an interesting borane complex here. Not really going through the mechanism here, but it does go on the less substituted side. Okay, that's one thing you do need to know. Non-Markovnikov. So take a moment. I gave you the same starting material, but different reagents, and try to predict the product for the following reactions. Hopefully you've had a chance to work with this. I messed up there, so step 1 and step 2. This one's not step 1, step 2, it's all at once, it doesn't matter. But hopefully you had a chance to work on this. And what did you get? So this is 1, 2, 3, 4, 5, 6, 7 carbons long. It's an alkyne. Oxymercuration, that makes me think I need to make a ketone. Okay? And it's okay if at first you drew this. But put brackets around it and then indicate to me that you do know it should end up like this as the final product, okay, where it tautomerized. Same thing with this one. You may have drawn me something that looks like this, but in the end, it will look like an aldehyde. 1, 2, 3, 4, 5, 6, 7. Okay, good. Don't add more carbons than you started with, right? Law of conservation of mass. Okie dokie. And then finally, I wanted to practice thinking backwards a little bit here. This is why it's important to know, like, what kind of functional group does this make, right? So I'm looking at the first one here, and it looks like I have an aldehyde. And I now know 2 ways to make aldehydes, right? Let's see if you remember. What was the way that we just learned in Chapter 8? Hopefully you said ozonolysis of a double bond. So if we do oxidative cleavage, we can get aldehydes. Or you just learned another one, which is hydroboration of a terminal triple bond. Okay? So you had 2 options there. This other one is a ketone. We know how to make ketones from, once again, oxidative cleavage, right, with ozone or potassium permanganate, or by doing by doing oxymercuration or even hydroboration of a triple bond, right? But this one's not a methyl ketone. It looks like an ethyl ketone. So it looks like we might have some trouble here trying to use oxymercuration or hydroboration, okay? I'll give you a second there, and when you get a chance, come back and check your work. Hopefully you've had a chance to check it. This one looks really easy. We can definitely do, you could do ozonalysis of a double bond, but it looks like we can also do hydroboration of the terminal triple bond. I have 1, 2, 3, 4 carbons here, so I have 1, 2, 3, 4 carbons here. Make sure you don't bend your triple bonds, you will lose points. It's a 180-degree bond angle. Okay? So it looks like I need a triple bond, and then what reagents do I need? BH3 and THF, good, and hydrogen peroxide, sodium hydroxide, or any sort of base, right? And the presence of water. Okay? That's all you need to get that product there, and that's the only product you'll get. Now the other one's a little bit harder. You might think, oh, well, oxymercuration, because we just learned it. However, if we try to do oxymercuration, it looks like it's 5 carbons long. 1, 2, 3, 4, 5. That would be our starting material, right? And we could make it, if the alcohol went on this side, on the third position, it'd be 1, 2, 3, 1, 2, 3. It'd be perfect, but we'd also have a mixture of products, right? Because the alcohol would go on this side too. So we have to fix that, right? There's another way we know how to make a ketone, and that is through oxidative cleavage, right? So we can go to a double bond. Oh, that just doesn't look very nice. So I'll draw this first. And then a double bond here, and then out, out, in. If I do oxidative cleavage of this particular double bond, I will get solely this product, which is good, which means you're going to be efficient and cost effective. That's the goal here. Okay? So for this one, the first step you're going to do is ozone, right? And the second step you're going to do is the zinc and the acid, right? To work it up. Now, many of you may have done KMnO4 and acid as the reagents, and that totally works fine too, because we're not making carboxylic acids or aldehydes here. We're going to make ketones no matter what. Okie dokie? So I'm going to stop at this slide here. Make sure you read the chapter up until this point. Practice those chapter problems, like the inner chapter problems, to ensure that you understand this, and then when you're ready, start the next lecture, which will wrap up the reactions of alkynes. Okay, good luck studying, and I will see you later.